Hi, we're Zion and Jonathan, and we are going to present a survey of hardware transient errors and error handling techniques. So first we present our problem, which is hardware transient errors. These are errors that are caused by external factors, and they happen rather irregularly. Despite the fact that they happen irregularly, they can still cause major issues. For example, in 2000, alpha particles corrupted the cache of servers hosted by Sun Microsystem, and what happened is it crashed multiple consumer sites such as eBay and AOL. In order to combat this, modern airplanes actually all have duplication built into their computing systems. However, nowadays, hardware transient errors have become even more common, and this is due to attempts to increase performance through increasing CPU frequency or through attempts to increase energy efficiency by reducing circuit voltage. So there are two major classes of error handling techniques. One is error analysis and tolerance. This is particularly useful for approximate computations, such as neural networks or financial applications, which can tolerate occasional errors in their execution. And if we actually understand the impact of hardware transient errors, these computations might be able to tolerate them, and we might not need to handle these errors at all. The relay analysis is a static compiler tool that is part of this class of techniques, and it measures program reliability. The second technique is error detection and correction. This can be done in hardware through error correction codes, parity bits, and duplicated functional units. It can also be done in software through instruction duplication. In this project, we implement and we evaluate the results of the relay analysis as well as the instruction duplication and how accurate they are. So as far as project achievements, we extended the GEM5 hardware simulator to simulate errors in the ALU and FPU executions. We evaluated the relay analysis on the GEM5 simulator, and we evaluated the instruction duplication method on the GEM5 simulator.
In order to simulate hardware transient errors, we extended the GEM5 simulator. The GEM5 is a full system hardware simulator that is widely used in research. In this project, we simulated a full system with a single GEM5 atomic simple CPU. It's an in-order CPU without instruction duplication, or SMP. And every clock tick, a micro IIC instruction is executed. We'll explain micro IIC instruction shortly. All other configurations are GEM5 default, such as cache, memory, clock, and voltage. We extended the GEM5 simulator with an error injection mechanism. We use that mechanism to simulate unreliable hardware with transient errors. Next slide. Here's how the error injection mechanism works. When a binary is executed on the GEM5 simulator, each x86 instruction is translated into several micro IIC instructions. After the execution of each micro IIC instruction, if it is ALU or FU related, we inject errors into the destination register. Here's the example on the right. The read instruction is translated into a load, an add, and a write instruction pointer. If the ALU is unreliable, the addition, after the execution of the addition of RSP, an error injection can happen. So the flow graph is shown at the right bottom. Next slide. Now we have our hardware simulator. Firstly, we analyze the relay analysis. The relay analysis is an intra-procedural compiler analysis that computes and reliability lower bound for a given function. It can analyze the impacts of unreliable ALU, FPU, and memory operations, and it can be used for certain approximate computations. In this project, we simplify things by assuming memory is fully reliable, but ALU and FPU can fail. We also formally define reliability as the probability that a component returns the correct value. The component can be an ALU, FPU, or a function, or a set of variables. Next slide. An example of the relay analysis is shown below. You have a very simple function. The relay analysis is able to infer that the return value depends on one ALU addition, one FPU type conversion, and one FPU multiplication. Therefore, the reliability of the return value is greater than or equal to the reliability of the input arguments times 2 FPU operations times 1 ALU operations. You can see that in practice, not every error will be observable in the final result. That's why the right-hand side is a lower bound. In this project, we're trying to answer the following two questions. Is this lower bound actually correct on our hardware simulator? If not so, why is it not correct? Next slides. To set up our experiment, we implement two benchmark applications. The first one is matrix vector multiplication, which is MATVEC. The second one is successive over-relaxation, SOR. Firstly, we run the two benchmark applications under different ALU and FPU error rate on the Gen5 simulator. For each configuration, we will run an application 5,000 times to measure the runtime reliability. Then, we manually apply the relay analysis onto the two benchmark applications to compute theoretical reliability lower bound. Finally, we compare the runtime reliability and the lower bound. Next slide. Here's a snippet of the experiment result. On the left, you have MATVEC result. On the right, you have successive over-relaxation. The yellow line is the reliability lower bound. The blue line is the runtime reliability of the application compiled without compiler optimization, clang-0. The red line is with compiler optimization, clang-01. You can see that under an unreliable FPU, the theoretical lower bound is correct and also exactly matches the runtime reliability behavior of MATVEC. However, under an unreliable FPU, under an unreliable ALU, the lower bound actually breaks. For a successive over-relaxation, under an unreliable FPU, the theoretical lower bound is correct, but also can be pessimistic. You can see that the runtime reliability behavior is significantly better than the lower bound. Under an unreliable ALU, the theoretical lower bound breaks again. You can also see that in certain cases, like on certain graphs, compiler optimization actually significantly improves the runtime reliability of the applications. Next slide. To summarize things up, under an unreliable ALU, we think the reliability lower bound actually breaks. One of the reasons is that the relay analysis assumes stack operations are fully reliable, but that's not the case in our simulator. We have a full explanation in our final report. Under an unreliable FPU, the reliability lower bound is correct, but pessimistic. We also think that in certain cases, compiler optimizations can improve the runtime reliability of application. Next slide.
Now we're going to go over our second error handling technique, which is instruction duplication. So as you can see on the right, what happens here is that every FPU instruction is executed twice. This execution is repeated until the two results match. However, this closure can actually still fail, mostly because this final comparison is still executed on the FPU. And as a result, an erroneous value of result can actually get by. Our major question then is, how effective is this method and what is the overhead of it? This is our experiment setup, and in this case, we have 4 benchmark applications. For each of these applications, we duplicate the floating point operations to create 4 hardened applications. We then run all 8 of these applications with various FPU configurations inside of the Gen5 simulator 5,000 times. So we get a measured application reliability for the original application, as well as a hardened reliability, and as well as the overhead for the hardened one for each of the hardened applications. We then compare these values. This is the results of our experiment. And as you can see across the board, all of the reliability gains are greater the lower the initial floating point FPU reliability. If we take a look at MATVEC, for example, on the top table, at 0.9605 FPU reliability, the overall program reliability increases around 2.55x, whereas at 0.9999, the reliability gains are negligible. However, this is different per application. So if you look at SOR on the bottom table, at a 0.9959 FPU reliability, we get around an 811.67x increase. This is largely due to the initial program having such low reliability. If you look at 0.9999 FPU reliability, however, SOR has around a 1.20x increase. However, on the other hand, if you look at the instruction count overhead, this remains fairly consistent across FPU reliabilities. So taking a look at MATVEC again, this ranges anywhere from 2.20x to 2.09x, which is fairly consistent. And SOR, which is very different across FPU reliabilities, if you look at it, the instruction count overhead is actually very similar, anywhere from 2.20x to 2.19x. So as a result, we see that the lower the FPU reliability, the greater the overall reliability gain is from instruction hardening. And at 0.9969 FPU reliability, for example, the application, per application, the gain ranges anywhere from 1.49x to 213.87x. What we see for overhead, on the other hand, is that regardless of the FPU reliability, the overhead stays consistently high, ranging from 1.53x to 3.04x. And we want to clarify that the reason we're using instruction count as a overhead benchmark instead of running time is because we are running on a hardware simulator. So since we're running on a simulator, actual running time is rather useless, but instruction count should remain the same versus when running on a simulator versus bare metal. We also believe that instruction count is proportional to actual running time because all of these applications are CPU intensive. We also present our YOLO v3 experiment. We mentioned approximate computations before, and this included neural networks. YOLO v3 is a neural network for object detection and classification for images. And theoretically, it should then be able to tolerate occasional errors. So we wanted to test how much error it can actually tolerate in its input images. These are the results of our YOLO v3 experiment. The top image is running YOLO v3 on an image with no errors. You can see it classifies many kites. The bottom is running YOLO v3 on an image with 0.2% errors. As you can see, most of the kites actually ended up going undetected, and one even gets misclassified as a bird. So this shows that even approximate computations can greatly benefit from instruction duplication. To conclude, our project presents a survey of hardware transient errors and related error handling techniques. We implemented and evaluated work from 2 different classes of error handling techniques, and we believe that our project ends up helping shape future research projects. Thank you for listening, and if you have any questions, please feel free to reach out to either of us. Thank you.